In this second to last section, we need to look at wave characteristics. We need to describe a wave pulse and a continuous progressive travelling wave. So, when we have a single ripple which travels on the surface of a pond, for example, this is a wave pulse. It's a single pulse of energy which is propagated through the medium. Or we could have a single pulse on a slinky. This is a pulse. It is good to look on the PHET website. They have a nice wave on a string demo. A continuous wave or a progressive wave is when the source oscillates with a periodic motion and it provides a continual cycle of periodic pulses, or in other words, a continuous progressive wave. The energy will spread away from the source and there will be a continuous flow of energy. So these waves, a progressive wave which starts from the source and moves away, is something that transfers energy. There is no net motion of the medium through which the wave travels. In other words, the particles that are part of the medium that transfer the wave oscillate around a fixed point, so there's no net transfer of the particles in the medium. The wave, however, is transferred. The particles move from side to side but go back to their original position again. Here we have a slinky demo. The particles move up and down and the wave goes to the right. With a longitudinal wave, however, the particles move from side to side in the same direction, or in the opposite direction, to the energy transfer. Describe and give examples of transverse and longitudinal waves. This is a longitudinal wave. What makes it longitudinal? This, for example, could be a sound wave. We have the red line could be the surface of a drum which is vibrating and sends a compression wave through the gas. The disturbance is in this direction, is parallel to the motion of the wave. Notice that the wave moves from left to right. The particles themselves move in the same direction and back again. So if you watch this one, for example, in the middle, fix your attention on one, you see it just moves to and fro, and does not actually get transferred to the right hand side. So the energy travels this way. The particle in the medium oscillates parallel to the motion of the wave. A transverse wave. Here we have the wave is moving from left to right, but the particles are moving up and down, so they move at right angles to the flow of energy of the wave. For example, light waves are transverse. The disturbance is perpendicular to the motion of the wave. So this is the transfer of the wave energy, but the oscillation is in the vertical direction, perpendicular to the transfer of the energy. Describe waves in 2 dimensions, including the concepts of wavefronts and rays. This was asked in one previous paper. So here we can see disturbances on the surface of a swimming pool or a pond. Let's look at a wave front. These lines show wave fronts here. These are a line. This is a line which joins neighbouring points that have the same phase or the same displacement. So this is all the same displacement, and they have to be neighbouring. This to neighbour this one. This is a wave away from it, a wavelength away from that. So this would be a wave front, for example. What about the ray? A ray is basically a mathematical line showing the direction in which the wave energy is travelling. So if you imagine that it starts here, the wavefront is here, it's actually travelling in this direction, always at right angles to the wavefront. So this would be the ray. Notice it's at 90 degrees to the wavefront.